Hello, everyone, and welcome to Lecture 18 of GPU Computing. Today, we're going to talk about graph processing. So last time, we spoke about sparse matrix computations. It was the second lecture in a series of 2 lectures about sparse matrix computation. In the first lecture, we had talked about 2 formats, COO and CSR. And last time, we talked about 2 more formats, which were the ELL format and the JDS format. So the ELL format looked like this. What we did is we grouped the non-zeros of the matrix, similar to what we did with CSR. However, instead of kind of linearizing them in row major order like we did with CSR, we actually added padding so that all the rows have the same number of non-zeros if you include the padding. And then we stored this table in column major order. So we stored it, we store the non-zeros along the column, followed by the next column, followed by the next column. And what they gave us is an array like this with the values, non-zero values, and the column indices. And the nice thing about this is that when each thread goes to access the first element of the row that it is responsible for when doing the SPMV, we can see that the threads are accessing nearby data elements, so the memory accesses are coalesced. However, we saw that one of the problems with ELL is all this overhead added from padding. And if we have these extra long rows, like here we have this second row and the second to last row are pretty long compared to the others, we end up having a lot of overhead from padding, and this take up a lot of space. So one way to regulate the padding, or to minimize the amount of padding that we have, is to have a hybrid ELL COO format where we have enough columns in this compressed table for most of the rows, but then for the very long rows, we have an additional COO format, COO representation just for the extra non-zeros in these rows. And by doing this, what we did is we were able to get the benefit of ELL format when it comes to memory coalescing, but then minimize the padding by processing the non-zeros in the very long rows separately. And then after that, we went to and looked at the diagonal storage format, which aimed at minimizing control divergence because ELL still has control divergence. And to do that, what we did is similar to CSR and ELL. What we did is we grouped the non-zeros. We grouped the non-zeros of the rows like this together. But then what we did to minimize control divergence is that we sorted the rows, and we kept this permutation vector that reminded us what the original row index of each new row is. And by sorting the rows, now when threads process adjacent rows, they're going to process rows of similar length, and this is what helps us reduce the control divergence. And then in order for us to achieve good coalescing, what we did is we stored these rows in column major order. So we went in this direction. So when we linearize arrays, as you can see, we have the values, we have the columns, we have the original row. We also have these offsets that tell us the beginning of each section or each iteration. And now when all the threads go to access the first element of their corresponding rows, as we can see, the accesses are coalesced. But not only that, also the threads that are in the same warp. So here the green and the orange thread down here. If you look at the rows that they're processing, these rows are of similar length, and this is what enables us to also have low control divergence when it comes to using the JDS format. So this was an overview of what we covered last time. Any questions about last time's material before we move on? Okay, so then today what we're going to do is we're going to talk about graph processing. And to talk about graph processing, I would like to first talk about how we represent graphs. So a graph, you guys are familiar with graphs. We have a bunch of vertices and they're connected with edges. And the way we can logically represent a graph is using an adjacency matrix. So an adjacency matrix is a way to represent a graph. And what we have is every row in the matrix represents the adjacency list of a source vertex. And the columns represent the destination vertices. And when I have a 1 in one of these cells in the matrix, what this says is that there's an edge from row 0 to, there's an edge from vertex 0 to vertex 1. When I have a 1 over here, this says that there's an edge from vertex 1 to vertex 3. Now, the adjacency matrix is usually very sparse. So what can we do to represent them? We just finished talking about sparse matrices.
We convert it to one of the formats.
Right, exactly. So we can, because the adjacent matrix is usually very sparse, we can use the same storage formats that we talked about with sparse matrices to also represent graphs. So we can store the adjacency matrix of a graph using any of the sparse storage formats that we looked at previously. Now, what we're going to focus on in today's lecture, just to keep things a little bit simpler, is we're going to focus on unweighted graphs. And since the graphs are unweighted, it means that all the values inside of this adjacency matrix are going to be 1, so we're not going to need to store them. We just care about whether there's a 0 or a non-zero. If it's a non-zero, then it's a 1. So we're not going to store any values in our representation. If this was a weighted graph, then we would have needed to store these some more values in this representation. So we would have needed somehow to represent them. But because we're focusing on unweighted graphs, we're not going to store the values. We're just going to keep track of whether there is a non-zero or there isn't a non-zero over there. The next thing is we're going to focus on undirected graphs. And what that means is that these matrices are going to be symmetric. Okay, so we'll be focusing on undirected graphs. But a lot of the concepts that we are going to talk about today equally apply to unweighted graphs, to weighted graphs, and they equally apply to directed graphs. But for simplicity, we're just going to be focusing on unweighted graphs and undirected graphs. Now we said that the adjacency matrix can be usually represented using the storage formats that we talked about so far. So let's see how we can do that. For example, we could use COO to represent the graph. In this case, the COO, remember with the COO in a sparse matrix, we had the row index, the column index, and the value. A COO representation of the graph is going to have the list of edges, right? So like in the sparse matrix representation, we had the list of non-zeros. So for a graph, we have a list of edges, and the arrays are gonna have the source vertex of each edge, the destination vertex of each edge. If it was a weighted graph, we would have also had a third array with the weight of each edge, but it's not a weighted graph, so we're not going to have that array. So here what this says is that I have an edge from 0 to 1, because I have an edge from 0 to 1. Here I have an edge from 0 to 1. It says I have an edge from 0 to 2, an edge from 1 to 0, an edge from 2 to 0, an edge from 3 to 1, etc. Okay? So this is a COO representation of this graph. We can also represent the graph using CSR or CSC. So in this case, if I wanted to do a CSR representation, then rather than having the source vertex indices, we would have source pointers. And these source pointers would point to the beginning of the edges, the outgoing edges of the vertex in this destination next array. So here what this is saying is that for the source vertex 0, its edges begin at index 0 in the destination array, and they end at 2, because this says here that the vertex 1, its neighbors begin at 2, which means that source vertex 0, its neighbors are going to go from 0 to 2, not including 2. So here source vertex 0 will start at 0, and its neighbors are going to be 1 and 2. As we can see, 0's neighbors are 1 and 2. Here 0's neighbors are 1 and 2. This is saying that vertex 2, its neighbors begin at index 2 in this array, and they end at index 5, not included. So here the neighbors of vertex 1 are going to start at 2, and they're going to be 0, 2, and 3. And the fifth one is not included. And as you can tell, 1 has the neighbors 0, 2, and 3. Here 1 has the neighbors 0, 2, and 3. Okay, so this is how we can use CSR to represent a graph. Now, like I said, we do not need to store any values because the graph is unweighted. But if the graph was weighted, we would have needed a third array in each of these representations to track the weight of each edge. And then also one thing to note is that CSR and CSC are equivalent because the matrix is symmetric, right? This matrix is symmetric because it's undirected. So the CSR and the CSC representations are equivalent because if I transpose this matrix, it's going to be the same. If the matrix was not symmetric, then the CSR and the CSC representation would not have been equivalent. Today, we're going to take advantage of the fact that CSR and CSC are equivalent in one of the optimizations that we can apply. And that's the reason why I'm making the assumption that the matrix is symmetric. But this is not necessary. If I did not make this assumption, I could have simply kept around both a CSR and a CSC representation of the matrix. Did somebody have a question?
Yes. So since the types of matrices we could have as input are so varied, how do we choose one method over the other? Is there a measure of the matrix that can tell us which would be more efficient?
So good question. So like we saw with sparse matrices, the format that we choose to represent the sparse matrix has high impact on the approach that we use. The format in sparse matrices, the format that we use to represent the sparse matrix has a high impact on the how we implement the kernel to process that sparse matrix, or to do the SPMV, which was the case that we're looking at. So similarly, the format that we're going to choose to represent the graph is going to have an impact on how we go about processing this graph in parallel. So yes, the choice of the properties of the graph are going to impact what is the best parallelization approach to use to process this graph. And naturally, that's going to have an impact on the choice of storage format that we have. And we will see examples of that throughout our lecture. Okay. Okay, so having spoken about how we represent graphs using the sparse matrix storage formats that we've seen before, the next question is, how do we parallelize graph processing? And I'm going to talk about, in general, various approaches to parallelizing graph processing, and then we're going to take these approaches and we're going to apply them to a specific graph problem, which is going to be breadth first search. Okay, but let's first start and talking in general about approaches to parallelizing graph processing. So there's there's two major approaches to parallelize a graph processing. One approach is the vertex-centric approach. And what the vertex-centric approach does is that it assigns a thread to do something for each vertex. Okay, so if I have a graph algorithm I'm trying to parallelize, what I do is I assign a thread to do something for each vertex. And these threads operate on these vertices in parallel. Obviously, they might need to communicate with each other. Obviously, I might need to have global synchronization. But the principle behind vertex-centric parallelization is that I have a thread do something for each vertex in my graph. Now, when I have a thread do something for each vertex, naturally that thread is going to want to visit the neighbors of the vertex, to look at who are the neighbors of that vertex. So if I want a thread to be able to go through the list of neighbors in a vertex, what's the best format for me to use? Is it COO or CSR?
COO.
Okay, think about it. I want a thread to be able to go and find all the neighbors of the vertex. This is similar to a thread wanting to find all the non-zeros in a particular row. So if I want a thread to be able to loop through all the neighbors of a vertex, would I want to represent it as COO or CSR?
CSR.
Right, CSR, because CSR is what gives me all the non-zeros of a particular row together in one chunk, right? So typically, if I am using a vertex-centric parallelization, I typically use the CSR or the CSC format, because with the CSR or CSC format, this gives me the accessibility of, given a vertex, it's easy to find all the vertex's neighbors. And by the way, depending on the computation, we might also use ELL or JDS as optimizations. I'm not going to look at that today, just for simplicity. We're going to be just looking at COO and CSR, but just keep in mind that in some cases where you're using CSR, you might even be able to use ELL or JDS to further optimize your access pattern. Okay, the next, the other alternative to vertex-centric parallelization for graph processing is edge-centric parallelization. And in an edge-centric parallelization, the way we go about parallelizing the operation we're performing on the graph is by assigning a thread to do something for each edge. Okay, so I assign a thread to each edge, and that thread has to perform some operation that involves that edge. Typically, this would involve looking at the source vertex and the destination vertex of the edge. So in this case, if I'm going for an edge-centric parallelization, what format would I probably want to use? COO or CSR? Right, COO. So here I would typically want to use COO. Why? Because COO, in sparse matrices, COO helps me with given a non-zero, find its row and column index. And in graphs, what that's equivalent to is given an edge, COO makes it easy to find the source and the destination vertices of that edge. Okay, so there's two major approaches to parallelizing graph processing. One of them is the vertex-centric approach, which typically uses the CSR or CST representation of the graph. If the graph is symmetric, these two are equivalent. Or there's the edge-centric parallelization approach, which typically uses a COO representation. Okay. Now, in some cases, I may actually need to keep around both a CSR and a COO representation. This is called a hybrid representation. And an example of this is in some graph algorithms, I might need, for example, to look at an edge, and for that edge, find the neighbors of its source vertex and find the neighbors of its destination vertex. Okay, so given an edge, find the neighbors of the source vertex and find the neighbors of the destination vertex. So here I need to be able to find the source and the destination of the edge. And for the source and the destinations, I need to be able to find their neighbors. So in this case, if I'm doing a computation that requires me to do something like this, then I would need to use both a COO and a CSR/CST representation. Okay. Now, breadth first search, which we're going to look at today, does not require this. So we're not going to look at this hybrid representation today. But who knows an example of a graph computation that would require me to do something like this? To look at an edge, find its neighbors, and then find the, look at an edge, find its endpoints, and then find the neighbors of the endpoints.
Breadth first search.
Now, breadth first search doesn't really require this, but are you guys familiar with triangle counting or K-clique decomposition? So with triangle counting, for example, I usually want to find the number of triangles that an edge is participating in. And what that means is I need to find the intersection of the common neighbors of the edge's endpoints, because the common neighbors of the edge's endpoints each form a triangle. So to do that, I need to intersect the adjacency lists of the edge's endpoints. So in this case, I would need to be able to find the edge's endpoints, which I would need COO for, and then intersect the edge's endpoints, which I would need CSR for. So that is where we might need to have both representations, but we're not going to look at that at this kind of computation today. Today, what we're going to do is we're going to look at Bfs, and we're going to look at vertex-centric and edge-centric parallelizations of Bfs. Okay. So, any questions about this before I start talking about Bfs? Oh, somebody's asking, where is triangle counting used? So triangle counting is used in places where you're trying to find, for example, communities inside of graphs. A triangle is a special case of something called a triangle is a three-clique. It's also a three-truss. So it's a special case of trusses and cliques, which are different ways of finding communities inside of graphs. So vertices in the graph that are all very closely linked to each other. Okay. Yes.
In the vertex-centric approach, I understood. You're trying to basically model the graph itself using each thread. But in edge-centric, what are you trying to do? Are you trying to follow the path the algorithm would execute in?
Okay, I'm not modeling anything here. All I'm saying is that when I do a vertex-centric parallelization, I do something for each vertex. I do an edge-centric parallelization, I have a thread for each edge, and I do something for each edge. What that thing is depends on the on the specific graph algorithm that I am applying. Okay, and I will do an example using breadth-first search of both of these, so hopefully that will make things more clear. All right? Yeah, you're welcome. Okay, so let's start with breadth-first search. So what is the objective of breadth-first search? The objective of breadth-first search, at least the breadth-first search that we're going to look at today, is to find the distance or the level of each vertex from some source vertex. So given a source vertex, I want to find how many edges all the other vertices are away from this source vertex. Okay, this is one possible thing I might want to do with BFS. Maybe I want to. Other things I might want to do is maybe construct a Bfs tree. So here the level would be the depth of that vertex in the tree. But what I'm going to do is I'm not going to keep track of the whole tree. All I'm going to do is I'm going to keep track of the level of each vertex that I visit during my BFS traversal. Anything else I would like to do, I can easily just extend what I'm doing to do it. But for simplicity, all we're going to do is we're going to find the level of each vertex, or in other words, the distance or the number of edges it is away from the source vertex. Okay, so how does BFS work? Well, we're going to start with some source vertex. Let's say this is my source vertex here. So this source vertex is going to be level 0. And what I would like to do is I would like to find the level of all the other vertices in the graph. Okay, I will initialize all the other vertices in the graph to have level infinity, which means that they're not reachable from this vertex. And then what I will do is on the first iteration, I will visit all the neighbors of the source vertex and label them as having level 1. So all these neighbors are going to be level 1. Okay, and then on the next iteration, I'm going to visit all the neighbors of these neighbors. Okay, and I will label those as level 2. So everything that's reachable from the neighbors is going to be labeled as level 2. And then I'm going to keep doing this until there are no more vertices visited. So on the next iteration, I'm going to visit all the neighbors of these level 2 vertices, and I'm going to label those as level 3. Okay, on the next iteration, I'm going to try and visit all the neighbors of level 3, but there aren't going to be any neighbors that are visited. So that is how I know that I am done doing my BFS. And any remaining vertex that I haven't visited is going to be considered unreachable. So the remaining vertices are going to remain at a distance infinity, which also means that they are unreachable. Okay. So this is what we're going to do. Now the question is, how do I do this in parallel? Well, let's recall there's different approaches to parallelizing BFS. One of them is the vertex-centric, the other is the edge-centric. There's different approaches to parallelizing graph algorithms, vertex-centric, edge-centric. We're gonna apply this to BFS. So we're gonna start by looking at a vertex-centric approach for parallelizing BFS. And there's actually two versions of this. There's two different vertex-centric approaches for parallelizing BFS. The first vertex-centric approach for parallelizing BFS is called the top-down approach. And the way this approach works is on every iteration, I'm going to launch a thread for every vertex. And I'm going to check if that vertex was in the previous level. I'm going to go through that vertex's neighbors, and I'm going to check all the unvisited neighbors and mark them as being part of the current level. Okay. And the reason we call this top down is if you think of BFS as constructing a BFS tree, then what we're doing is we're assigning a thread to every parent in a vertex in the tree, and that parent vertex is finding all its children vertex in the tree. So it's making its way from a top level to a bottom level. This is why we call this a top-down approach. Okay, so let me show you what this looks like in an illustration. So here, if I'm on the iteration that is where level 1 is the previous level, and I want to find all the level 2 vertices. What I will do is I will launch a thread for every vertex. So I have a thread assigned to every vertex in the graph. This thread will check if the vertex is in level 1, and if the vertex is in level 1, so here, these 4 threads over here are the ones that will find that the vertex they own is in level 1. And if for these vertices that are in level 1, what the thread will do is it's going to loop over the neighbors of these vertices. And if the neighbors are not visited, it's going to mark the neighbors as being part of level 2. So this thread here is going to go through its neighbors. This neighbor is not visited, so it marks it as level 2. This neighbor is already visited, so it doesn't do anything. This neighbor is already visited, so it doesn't do anything. Okay, this thread over here is going to look at this neighbor, it's going to mark it as level 2 because it hasn't been visited. It's going to look at this neighbor, mark it as level 2. It's going to look at this neighbor and mark it as level 2. By the way, here, these 2 threads both find that this neighbor is level 2, but that's okay. Okay, as long as one of them finds it, that's fine. If both of them find it and label it as level 2, that's okay. That's not a problem. All right, so this is how the vertex-centric top-down BFS works. Each thread will find if its vertex is in the previous level. In this case, that's level 1. And if it is, it's going to go through its neighbors, and if they're not visited, mark them as being part of level 2, which is the current level. Okay, so having said this, let's go and implement this using Cuda. So I'm going to switch over to the code terminal over here. I've already set up the code to do all the host management stuff for us. So here I'm allocating, I have a CSR graph that's already been read from a file. I'm allocating it on the GPU, and then I'm copying it down here to the GPU. Okay, and then down here, I'm going to have a loop that's looping over the levels, and that calls a kernel to process each level. Okay, the reason is that I need to have a global synchronization across the different levels. Okay, so I'm going to have a kernel called for every level, and this kernel will process that particular level. And I'm also going to have this new vertex visited flag that's going to tell me whether a new vertex was visited on a particular iteration, so that I can know when I stop iterating across levels. Okay, so up here in my BFS kernel, I'm going to take a CSR representation of the graph. I'm going to take, again, the reason I need a CSR representation of the graph is because I'm using a vertex-centric parallelization. I'm going to have the level of each vertex. So this is kind of the label that tells me whether the vertex is visited or not and what its level is. I'm going to have this flag that I need to set if I visit a vertex, so that I know when I should stop iterating. And I'm also going to have the current level that I'm processing. So in this case, the current level is going to be level 2. Okay, meaning I'm finding out all the vertices that are in level 2. Okay, so let's start by implementing this. So what we said is, in the vertex-centric approach, we're going to assign a thread to each vertex. So down here, when I called this kernel, when I configured the number of blocks use the number of vertices to determine how many blocks I'm going to launch. Okay, so I have enough threads to process each vertex. So my first step is for the thread to figure out which vertex it's responsible for. And to do that, I'm going to write unsigned int vertex is equal to, I'm going to use the thread index as the vertex number. Okay, so thread 0 is going to be responsible for the vertex 0, thread 1 is going to be responsible for vertex 1, thread 2 responsible for vertex 2, etc. So I'm going to write unsigned int vertex is equal to block index.x times block dim.x plus thread index.x. You guys should be familiar with this by now. And of course, because I could have excessive threads in the last block, I need to have a boundary check. So I'm gonna need to check if this vertex is actually within bounds. To do that, let me go and look at how the CSR graph is represented and what information it gives me. So here I'm going to open. This is how the CSR graph is represented. I have the number of vertices, the number of edges, the source pointers. This tells me where the neighbors of each vertex begin, and then the destination, which tells me the neighbor of each of the source vertices. Okay, so here I'm going to check if the vertex is within bounds. I'm going to write if vertex is less than graph dot num vertices. Okay, and now that I have assigned a thread to each vertex in the graph, what does this vertex need to do? Well, first, the thread needs to check whether the vertex that it's responsible for is in the previous level. Okay, because only the threads in the previous whose vertices were in the previous level are going to loop over their neighbors to add them to the next level, to the current level. All the other threads are not going to do anything. So here I'm going to need to check if the level of my vertex, okay, is equal to the current level. Okay, so if the level, if to the current level minus 1, because here the current level is level 2, so I want to check I want the threads to be assigned to the vertices in the previous level. So any thread whose vertex is in level 1 is in the previous level, I'm going to add its neighbors to the current level. So here I'm going to check if level of vertex is current level minus 1. If this is the case, then the thread needs to loop over its outgoing edges and visit the neighbors at the destination of the outgoing edges. So how do I loop over the outgoing edges? Where do I find where my outgoing edges start and end? What do I use from up here? So remember, this is a CSR representation of the graph. So the source pointers are going to tell me where the neighbors of some vertex begin, or some source vertex begin. Okay? So what I will do is I'm going to loop over the outgoing edges. So I'm going to write for unsigned int edge is equal to CSR graph dot source pointers of vertex. Okay, so this tells me where the neighbors of the vertex begin, of the source vertex begin. How do I know where the neighbors of the source vertex end?
It's the next vertex minus 1.
Right. It's where the neighbors of the next vertex begin. So I'm going to write edge is less than CSR graph dot source pointers of vertex plus 1. Okay, and then plus edge. All right. So now here I'm looping over the outgoing edges. Okay, now for each outgoing edge, I want to find the neighbor that edge takes me to. How do I know the neighbor that the edge takes me to? Well, that's part of the destination array. This destination array tells me the destination of the edge. Okay, so I'm going to write unsigned int neighbor is equal to CSR graph dot destination of edge. So here now I have the vertex. I'm looping over its neighbors. Okay, and now what I need to do is I want to check if the neighbor was visited. If the neighbor has already been visited, I'm not going to do anything. If the neighbor has not been visited, then what do I want to do? I want to add it to the current level. So I'm going to check if the neighbor is visited. To do that, I'm going to look at the level of the neighbor. So if the level of the neighbor is equal to infinity, and here I'm representing infinity as uint max. Okay, uint max is the largest possible unsigned int value. Okay, so if the level of the neighbor, if the neighbor has not been visited, okay, then what I want to do is I want to add the neighbor to the current level, or I want to mark the neighbor as being part of the current level. Okay, so I'm going to write level of neighbor is equal to the current level. And what I need to do is I need to set this new vertex visited flag in order to indicate that I have visited a vertex, so that I can tell the host that we're going to have to do another iteration because we've visited a new vertex. Okay, so I'm going to set the new vertex visited flag to 1. Okay, so to summarize, I assign a thread to every vertex. I check if the vertex is in the previous level. If the vertex is in the previous level, I loop over its neighbors. And for each neighbor, I check if the neighbor has not been visited. If the neighbor has not been visited, I mark the neighbor as being part of the current level. Okay, any questions about this? Is it clear to everyone?
Yes, Professor. Just one question. This algorithm seems like it has a lot of if and for, and the for loop is not looping all the time up until the same value. So won't we have a lot of how is it called, divergence?
You're absolutely right. We will have a lot of control divergence, and we will talk about that. So you're absolutely right.
Okay.
Yes.
So
just
if it's a fully connected, sorry.
Go ahead.
If it's a fully connected graph, this algorithm would be very, very efficient, or it doesn't matter?
If even if it's a if it's a fully connected graph, then your BFS is just going to end in one iteration, right? Because everything. But I mean, if there's high connectivity in the graph, then what's going to happen is you're going to have a lot of control divergence because you know this is going to be a very long loop for some vertices, but not others. Okay, and we will talk about that. So please hold on to that question, and I will definitely revisit this topic. Okay, so now let's go and compile this code and run it and see what kind of performance improvement we get. So I'm going to compile, and I'm going to run. Okay, and as you can see, the kernel time is actually quite slow, right? Even slower than the CPU, by the way. Okay, and that's not including copy time. So the kernel time is actually quite slow for this. Okay, so let's see how we can improve on this. Let's see how the other approaches are going to compare. Okay, as I said, we looked at the vertex-centric top-down approach. Okay, and this is here is the code that we wrote. The other approach, the other vertex-centric approach besides the vertex-centric top-down approach is the vertex-centric bottom-up approach. And what the bottom-up approach does is for every vertex, it checks if that vertex has not been visited. And if that vertex has not been visited, it's going to check if any of its neighbors are in the previous level. And if any of the neighbors are in the previous level, it's going to add that vertex to the next level. Okay, so in the top-down approach, the threads were responsible. The threads that were active were the ones that were assigned to to vertices that were just visited. Whereas now the threads that are going to work are the threads assigned to vertices that have not been visited, and they're going to find out whether these vertices should be in the next level. So here, my threads are working on the vertices that are in the previous level. Here, my threads are working on the vertices that are potentially in the next level. And the reason we call this bottom up is here you can think of the threads are being assigned to every potential child vertex in the Bfs tree and figuring out whether this vertex, looking towards the vertices parents to find out if any of the vertices parents were in the previous level. Okay, so we're kind of at the bottom looking up at the previous level, and this is why we call this a bottom-up approach. Let me illustrate what I mean by this. In the bottom-up approach, what's going to happen is I'm going to assign a thread to every vertex, but then the threads that are going to work are the threads that are assigned to vertices that have not been visited yet, okay, as opposed to the vertices that are in the previous level. I'm going to assign threads to all the threads that will work are the threads assigned to vertices that have not been visited yet. And what these threads will do is they will go through their neighbors and they will find if any of their neighbors are in the previous level. And if they are, they will add the vertex to the next level. So here, this thread will find that one of its neighbors is in the previous level. And when it does that, it adds a vertex is responsible for to the current level. And notice that the minute this thread finds that one of its neighbors is in the previous level, and it adds its vertex to the current level, it actually doesn't need to continue looking at all the other neighbors, okay, because that's not really going to help. So the minute that the thread establishes that this vertex is in the current level, it can stop. It doesn't have to finish going through all its neighbors, which is different from the top-down approach. In the top-down approach, if a vertex was in the previous level, I had to go through all of its neighbors to find out if they were going to be in the current level. But what you will notice here is that I have these other threads out here are assigned to vertices that are not going to be in the current level. So these threads will actually loop over all of their neighbors, and they will find out that none of their neighbors are in the previous level. So they will not add the vertex they're responsible for to the current level, but they will have to loop over all of the neighbors. Okay? Is the bottom-up approach clear to everyone? Is it clear what every thread is doing? And is it clear how this is different from the top-down approach? Yes, question?
Yes, so bottom up is less work efficient than top down, right? Because you're doing useless work.
Work efficiency is related to work efficiency is a different concept. I think what you mean to say is that the bottom up, the top down approach. So the bottom up does more redundant work than the top down. Is that what you mean to say?
Yeah, maybe. Okay, I was confused.
It actually depends. It depends how many vertices. The amount of redundant work done depends on the graph. It depends on how many vertices have already been visited and how many vertices have not been visited. It depends on the number of vertices in the previous level. So this stuff depends. But I don't want you to confuse redundant work with work efficiency. Work efficiency was about given the sequential algorithm, does the parallel algorithm do as much work as the sequential algorithm or not? Okay, so I could implement a sequential algorithm that does exactly this. Okay, and in this case, the work efficiency will be the same. All right. So it's not here. It's not about it. I think you're observing that there's redundant work happening, which is true. There is, and we are going to also address this topic later on in the lecture. But that's a different concept from work efficiency. Okay, but good observation that there is redundant work. Any other questions about the bottom-up approach? Is it clear to everyone?
And Professor, I just wanted to know, how do you make sure that the graph that the search is complete? I disconnected at that moment.
Okay, so remember how we had a flag? I showed it before when I implemented the top-down kernel, and I'll show it again when I implement the bottom-up kernel. But remember how we had a flag that where we set it to 1 if we visited a new if we visited a new vertex. So by setting that flag, on the iteration that we don't visit any new vertices, that is how we know that we're done.
Oh, okay. Thank you.
Okay, so I'll point out that flag again when we implement this version.
Okay, thank you.
Okay, all right. So let's go now and implement this version. So I'm going now, and I'm going to go to Vertex-centric bottom up, and let's implement this kernel. Now this kernel, the source code is going to be, the host code is going to be all the same. We create the graph, we copy the graph, we launch as many vertices as there are we launch as many threads as there are vertices. But the difference here is what the vertices are going to do. So the only difference is going to be the kernel itself. Okay, so like with the top-down approach, I'm going to assign a thread to every vertex. So I'm going to use the thread ID as the vertex number. Thread 0 will be assigned to vertex 0. Thread 1 will be assigned to vertex 1, etc. So I'm going to write unsigned int vertex is equal to blockindex.x times blockdim.x plus threadindex.x. And I'm going to check that my vertex is within bounds. Again, let me open the CSR graph. So we're still using the CSR representation because this is also a vertex-centric approach. And here I'm going to check that the vertex is less than the number of vertices in the graph. Okay. All right. So now that I've checked that, now that I've assigned a thread to a vertex, now what I need to do is I need to check if my vertex has been visited or not. If my vertex has been visited, I don't need to do anything. If my vertex has not been visited, that's where I'm going to loop over my neighbors to check if any of them are in the previous level. So here I'm going to check if if my vertex has not been visited. In other words, the level of my vertex is equal to uint max. Okay, So if my level is still uint max, that means the vertex has not been visited. In this case, I want to loop over my neighbors and check if any of them are in the previous level. So how do I do that? Well, same thing we did before for unsigned int edge is equal to CSR graph dot source pointers of vertex. Edge is less than CSR graph dot source pointers of vertex plus 1, and then plus edge. And then for each edge, I'm going to find the neighbor at the destination of that edge. So I'm going to write unsigned int neighbor is equal to CSR graph dot destination of edge. And now that I have the neighbor, what do I need to check? I need to check if my neighbor is in the previous level. If my neighbor is in the previous level, I'm going to mark myself as being part of the current level. If my neighbor is not in the previous level, I'm just not going to do anything. Okay? So if the level of my neighbor is equal to the previous level, which is current level minus 1, then what I will do is I will mark myself as being part of the current level. So I will write level of vertex is equal to current level. And this answers the question that you asked. I have this flag over here that I need to mark to indicate that on this iteration I have visited a new vertex. Okay. If I don't visit a new vertex on this iteration, that is how I know that I am done. So if this flag never gets set, that means no new vertices were visited this iteration, which means my BFS is done. But as long as this flag is set, it means I'm going to have to launch this kernel another time in order for me to do the next iteration. Okay, now one additional thing I can do, which I haven't done before, is the minute that I find a neighbor that's in the previous level, and I mark myself as being in the level, I don't need to continue going through my neighbors. So here, if this thread checks this neighbor, finds the neighbor is the previous level, it can mark its vertex as being in the current level. It doesn't have to go and check the other vertices anymore. So what it can do is it can break. All right. So what we can do is we can break. Now, when we break over here, the advantage of this is that I'm going to exit this loop early, which means that I'm going to have less control divergence than I had with the top-down approach. In the top-down approach, the thread looped over all the neighbors, whereas in the bottom approach, I only loop over the neighbors until I establish that I am in the current level and I can break, right? The threads that will loop over all their neighbors are going to be the threads that are not in the current level. Clear? Any questions about this?
Professor, I don't see how this guarantees less control divergence, because I mean, even though you're breaking from the loop, like the other threads might not be breaking from the loop, or they might be breaking at a later time. So like for me, it's still the same level, or even worse.
Yes, you're right. But think of the for example, think of a vertex that has a very large neighbor list. In the top-down approach, when it's that vertex's turn to be processed, you're going to have to loop over all that entire neighbor list. In the bottom-up approach, when it's that vertex's turn to be processed, you're going to loop over because you have a very large neighbor list. You have a high probability that one of these neighbors has been visited. So you're most likely not going to have to go through that entire neighbor list.
Okay, thanks.
Okay. Yeah, you're welcome.
So this performs very well when you have, for example, one row that is quite large compared to the others.
Let's wait and see. I'm gonna yes, this will perform better when you have high degree vertices, and let's wait and see how well this performs. But yeah, and yes, what you're saying is accurate. Okay, so let's compile this and run it. Okay, so as you can, just as a reminder, the top-down approach took 12 milliseconds, and now we're going to run the bottom-up approach, and this time we took 2.9 milliseconds. Okay, so it's significantly faster than the top-down approach. Okay, because as we saw, this approach is able to exit early. It doesn't have to loop over all of the neighbors. Okay. All right, so this here is the code that we wrote. Now, one thing to keep in mind, when I said vertex-centric, I said there's two versions. There's actually another version, which is not really a different version, but we have something called a direction-optimized Vfs. And the direction-optimized Vfs does a hybrid of these two. And the direction it does is that it starts with the top-down approach and then switches to the bottom-up approach. Why? For the top-down approach, when I have a small number of neighbors in the previous level, right, I'm going to do a little bit. The top-down approach only goes through the neighbors in the neighbor list of the neighbors in the previous level. So in the initial iterations, I have very few neighbors in the previous level. So the top-down approach is going to do very little work. Whereas in the initial iterations, when I have very few neighbors in the previous level, the bottom-up approach is going to do a lot of work. Why? Because the bottom-up approach is going to check for all the unvisited vertices, whether any of their neighbors are visited. Well, when I'm at the beginning, I have very few visited vertices, so I'm going to have a lot of vertices that are not visited, that the bottom approach is going to go through their neighbor list. And because they have few vertices that have been visited, there's a high probability that these vertices whose neighbors I'm going through are not going to find neighbors that have been previously visited. So in the initial iterations, the bottom-up approach performs poorly. Okay, the bottom-up is inefficient at the beginning because most vertices will search all their neighbors and not find any neighbors that are in the previous level. Whereas in the initial iteration, the top-down approach is going to do very little work because there are few vertices in the previous level, so it's only going to loop over the neighbors of those vertices. So a direction-optimized Vfs starts with a top-down approach and then switches to the bottom-up approach later on. So let's go see how well the direction-optimized version performs. So here I'm going to go to the direction-optimized version. I've already set up the code for the direction-optimized version. There's nothing additional to implement in terms of the kernels. We have the top-down kernel that we implemented and the bottom-up kernel that we implemented. And if we scroll down here, the loop that's looping over the different levels and calling the kernels, it calls the top-down kernel for the first level, and then it's going to call the bottom-up kernel for the remaining levels. Okay, so let's compile this code, and we will run it. And as you can see, the direction-optimized version performs substantially better than the top-down version or the bottom-up version set on their own. Because the top-down version does substantially better than the bottom-up version in the first iteration or the earlier iterations, whereas the bottom-up version does better on in the later iteration. Why? Because as we said, at the beginning, most of the vertices have not been visited yet. So in the bottom-up version, in the beginning, most of the vertices are going to search all of their neighbors, and they're not going to find any neighbors in the previous level. So they would have done all that work for nothing. Whereas in the beginning, the top-down version is just going to loop over the neighbors of the one source vertex, or if it's the next level, a few source vertices, and it's going to visit their neighbors. That is why the top-down version does better in the initial iterations, while the bottom-up version does better in the later iterations. Okay? Any questions about this? All right, now let's move on to the edge-centric approach. So in the edge-centric approach for BFS, what we're going to do is we're going to launch a thread for every edge. And then for every edge, we're going to check if the source vertex of the edge is in the previous level, then we're going to, and the destination vertex of the edge has not been visited, then we will add the destination vertex to the current level. So in other words, here when level 1 is my previous level and level 2 is my current level, then what I'm going to do is I'm going to assign a thread to every edge in the graph, and the threads that are going to do the main work are the threads that are assigned to a vertex whose previous, that are assigned to an edge whose previous vertex is in the previous level, whose source vertex is in the previous level, and whose destination vertex has not been visited. So in this case, this thread will find that its source vertex this thread for its edge, it'll find that the source vertex is in the previous level, level 1, and its destination vertex has not been visited. So this thread will mark its destination vertex as part of the current level, which is level 2. Okay, is it clear? All right, let's go implement this. So I'm going to go down, and I'm going to the edge-centric approach. We're going to open the kernel, and we're going to implement this. So here, again, the host code is very similar, except that I'm going to be using a COO graph instead of a CSR graph. So here, when I allocate and copy the graph, it's a COO graph. Why is it a COO graph?
Because you are using edges, it's more efficient. We can find
right. I'm using the edge-centric approach. Right, I'm using the edge-centric approach. So given an edge, I want to find the source and the destination vertex. So a COO graph gives me that accessibility. So here, just let me recap on what the COO graph entails. Here, the COO graph is going to have the source vertex and the destination vertex for each vertices. I don't have any source pointers. Okay, if I scroll down over here, you'll find that when I am launching the BFS kernel, this time the number of blocks is configured based on the number of edges as opposed to the number of vertices. So I'm assigning a thread to every edge instead of a thread to every vertex. So I will start by assigning a thread to every edge. So thread 0 will process vertex 0, will process edge 0, thread 1 will process edge 1, thread 2 will process edge 2, etc. So in general, my edge is going to be equal to my thread index. So I'm going to write edge is equal to blockindex.x times blockdim.x plus threadindex.x. And then I need to make sure that the edge is in bounds, of course. I'm going to do if edge is less than COO graph dot num edges. So here, if my edge is within bounds, now what do I need to do? Well, I need to find my source vertex. I need to find my destination vertex. Okay, so I'm going to find unsigned int the vertex is equal to COO graph dot source, the source vertex of the edge. I want to find the neighbor. Okay, so I'm going to have unsigned int neighbor is equal to COO graph dot destination of edge. Okay, so the vertex is the source of the edge, the neighbor is the destination of the edge. And now, if my source vertex is in the previous level, I want to mark the neighbor, and the neighbor has not been visited. I want to mark the neighbor as being part of the current level. So how do I do that? I'm going to check if my vertex is in the previous level. So if level of vertex is equal to the previous level, which is the current level -1, and if my neighbor has not been visited, so if the level of my neighbor is uint max, this means my neighbor has not been visited. Oops. And in this case, what I would like to do is I would like to mark my neighbor as being part of the current level. Okay, so I'm going to write level of neighbor is equal to the current level. And I need to, of course, set the flag that indicates that I visited a new vertex on this iteration to make sure that I launch another iteration later on. Okay, so I'm gonna set this flag to 1. And what you notice here is that there are no loops. Every thread is responsible for one edge. So either it visits a neighbor or it does not visit a neighbor, but it's not looping over any neighbors. And you can probably expect that this approach will have less controlled divergence, just like when we use COO to parallelize SPMV, it had less controlled divergence than when we use CSR. Okay, so let's compile this and run it. So remember, my top-down vertex-centric approach was around 12 point something milliseconds. My bottom-up approach was 2.8 something milliseconds. Notice these times are a little bit different from what we saw at the beginning of the lecture, just because I had to run them again because we had a glitch in the middle of we had a connection problem in the middle of the lecture, so I apologize for that. And then here I have 1.1 milliseconds. So now I'm going to compile this code that we just wrote, and I'm going to run it. And as you can see, we have around 1.68 milliseconds. So the edge-centric approach is better than the top-down and the bottom-up approaches. Okay, zoom out. So this was the time for the top-down. This is the time for the bottom-up. So the edge-centric approach was better than the top-down and the bottom-up approaches. Direction optimized actually did better than the edge-centric approach, but you can tell that the edge-centric approach does fairly well. Okay, any questions about this?
Professor, in the
Yes.
when we looked at the source and destination of the edge, is there an entry for both directions since the graph is undirected?
Yes, there is an entry for both directions.
Oh, okay.
So
So
here
that's
I'm not storing only one direction of each edge. I'm storing both directions. So here, in fact, I'm glad you asked that. This illustration is a little bit deceiving. There's actually going to be two threads here. There's going to be a thread for this direction. There's going to be a thread for the other direction. So I thank you for asking that. But I'm only including one thread here for simplicity. But you're right that there's going to be two directions. There's going to be two edges, one in each direction. And there's going to be two threads, one for each edge.
Professor, using this approach, aren't you exhausting the number of threads very fast? Because you might have for each node two or more edges. So each time you're adding two times two times two times two. So it will exhaust all the threads very fast, no?
So you're right. These approaches are using a lot of threads. And a lot of times, a lot of these threads are not doing anything. They're just checking and realizing that they're not relevant for this iteration and they're exiting. So I will talk about that. So hold on to that question. I'll revisit this topic. Okay, so this was, so as you can tell, the edge-centric approach and the bottom-up approach did pretty well. The top-down approach did not do that well. The direction-optimized approach did pretty well. And this is the code that we just wrote. So now we want to talk about the data set implications. So this is something that you guys have been alluding to, which is that, doesn't the shape of the graph, some of you asked, doesn't the shape of the graph affect the choice of storage format, the choice of parallelization? And it does. So the best parallelization approach depends on the structure of the graph. The graph that I've been using since the beginning of the lecture is actually it's a social network graph. So it's a high degree graph. Okay, you have a lot of these high degree neighbors. And the vertex-centric bottom-up approach, as well as the edge-centric approaches, are better on high degree graphs, such as social network graphs where you have these celebrities. And the reason they're better on high degree graphs is that they're better at dealing with load imbalance. On the other hand, the vertex-centric top-down approach, which we saw performed pretty badly on the high degree graph that we've been using, actually performs better on low degree graph. Okay, and what's an example of a low degree graph? Where do we find low degree graphs in real life?
A map?
Right, exactly, a map. And in fact, I have a map graph over here that we can use. So let me go back and show you how each of these versions performs on a road graph. So I'm going to go back. Actually, we'll do the edge first. I'll do them in reverse order. So here I'm going to do Bfs, but this time I'm going to do it on a road graph. This is the road graph for California. So I'm going to run BFS on the road graph. This is a bigger graph than the one we had before, so it's going to take a little bit longer to run. Okay, so we have 234 milliseconds for the edge-centric approach. Let's go to the direction optimized approach. Remember, the direction optimized approach was doing top down for the first iteration and then bottom up for the rest of the iteration. So most of it is just bottom up. So here I'm going to run BFS on the roadmap. Again, we have around 228 milliseconds, so a little bit better than edge-centric. Let's go to the vertex-centric bottom-up approach. And again, we have around 204 milliseconds, so it's a little bit better than the edge-centric approach. Remember, for the high degree graph, edge-centric was better than the bottom-up vertex-centric. Here, the vertex-centric, the bottom-up is better than the edge-centric. Now let's look at the top-down approach. And what do you notice? It's significantly faster. So this vertex-centric top-down approach that was much slower for the high degree graphs, almost 4 times slower for the high degree graphs, or 4 to 12 times slower for the high degree graphs, is actually much faster than these other approaches for the low degree graph. Okay, and the reason is that with the low degree graphs, you only do work for the vertices that have been visited on the previous iteration. And with the low degree graphs, the number of vertices that are visited each iteration are very small because my graph has low degree. Or they're not necessarily very small, but they're smaller than the case with the high degree graph. You have more iterations and fewer vertices per iteration. And that is why the top-down approach does better in the case of low degree graphs. So here, the vertex-centric top-down approach is better on low degree graphs. For example, maps of roads in a geographic area. Okay, and in fact, when we're applying vertex-centric to high-degree graphs, there's actually an additional optimization that we can do, which is we can launch, whenever we encounter a high-degree vertex, we can launch more threads to process the neighbors of high-degree vertex. And we'll cover later how we can launch more threads. But the key takeaway here is that the choice of the best graph depends on the data set. Sorry, the best graph algorithm, the best approach depends on the data set. So there's no best BFS algorithm that's good in all the data sets. You really need to consider what kinds of data sets you're running on when picking the algorithm that you want to use. Okay. All right. Another important topic I would like to talk about today is the similarity between BFS and SPMV. So just like when we store graphs in a similar way to how we store sparse matrices, I want to talk about how BFS is similar to SPMV in how we access data. So let's go back and look at what SPMV does. In SPMV, what we did is we looped over the rows for every row. So here we're doing these rows in parallel for every row, and then for every non-zero in that row, we looked up for that non-zero the element at the course with the vector, the element in the input vector at the column index, and then we updated the element in the output vector at the row index. Okay. So here's what we did with SPMV. Well, let's look at what we were doing with BFS, and in particular, I'm going to look at the vertex-centric bottom-up approach of BFS. So in the vertex-centric bottom-up approach of BFS, what did we do? Well, what we did was for every vertex, which is kind of like for every row in SPMV, and then for every edge of that vertex, so for every edge in that vertex, which is like for every non-zero in the row, okay, we looked up the old level of the neighbor, okay, which is like looking up the input vector at the column, and then we updated the new level at the vertex for the vertex itself, which is like updating the output vector for the row at the row index. You can tell that these two ways of going through my data, okay, are actually very similar. And in fact, there are also corresponding ways of performing SPMV that look similar to the vertex-centric top-down approach, as well as the edge-centric approach of performing BFS. Okay, having seen this, you can tell there's a very close correspondence between sparse matrix operation and graph operations, particularly here between SPMV and BFS. And this brings me to the topic of the linear algebraic formulation of graph problem. With a few tweaks, we can actually formulate BFS exactly as SPMV. To do that, what we would need to do is we would need to use the visited list as the input vector and the output vector to SPMV. And we would need to have a few other vector operations to get exactly what we want. But in general, SPMV would remain the dominant computation if we want to formulate BFS as SPMV. Now, what's the advantage of us formulating BFS as SPMV? In fact, many graph problems can be formulated in terms of sparse linear algebra computations, not just BFS. And the advantage of formulating graph problems in terms of sparse linear algebra computations is that there are many sparse linear algebra libraries out there. So when you formulate your graph problem as a sparse linear algebra problem, what you can do is you can leverage mature and well-optimized libraries for doing high-performance sparse linear algebra. Okay, so this is an advantage of linear algebraic formulations of graph problems. And also, linear algebra operations tend to be very nice and easy to parallelize. Now, the disadvantage of this approach is that it's not always the most efficient approach to solve a graph problem. And this brings me to a topic that you guys have been mentioning throughout the lecture, which is redundant work. So the approaches that we've discussed so far, what they do is they're checking every vertex or edge on every iteration. So the vertex-centric approach checks every vertex on every iteration. So we launch a thread for every vertex on every iteration. The edge-centric approach is launching a thread for every edge on every iteration. So the approaches we've discussed so far check every vertex or edge on every iteration to see whether they are relevant for this iteration or not. The advantage of this is that this is easy to implement. It's highly parallel. It's very easy to extract parallelism this way, and also we don't have to synchronize across threads. Okay, all the threads here were operating completely independently of each other. None of the threads had to talk to the other threads and synchronize with them and communicate with them to figure out what they were doing. The weakness of this approach, like you guys have been observing, is that we are doing a lot of unnecessary work, because many threads will just find that their vertex or edge is not relevant for this iteration and they will exit. So what we will do next time, so this lecture is to be continued, what we will do next time is we're going to see another approach for parallelizing BFS. But this time what we will try to do is we're going to try and avoid launching threads for irrelevant vertices or edges. Instead, what we're going to do is we're going to construct the frontiers of the edges that are relevant, and we're going to try and only process the vertices or the edges that are relevant for that particular information. We're going to try and only launch threads for the vertices or edges that are relevant for that iteration. And this is going to reduce the amount of redundant work. But of course, because we need to be constructing these frontiers, it's going to require more synchronization across threads. So there's going to be this trade-off between parallelism and avoiding synchronization, and between reducing redundant work. And we will look at this trade-off next time. Okay, so you can read more about what we covered today in chapter 12 of the textbook, and we will continue the later sections of chapter 12 in next time's lecture. Does anybody have any final questions before we conclude? All right, if not, then that's all for today, and I will see you next time. Bye, everyone.